everyone. Welcome to the last session of this conference. Today we have 6 oral presentation and 6 poster presentation. The first presentation, please let's look at. The presenter are Pınar Taşlı and Aykut Demirçalı. And the topics: investigation of properties of new disazodides derived from anemone pyrrhizodoles by DFT method. Pınar, is here Pınar?
Pınar Tunay Taşlı.
Yes, evet.
Yes, I am here.
Okay, we can start, Pınar. You can share your presentation first.
You can start video. I sent you a video for my presentation.
Okay.
Okay.
Okay.
Hello, my name is Pınar Taşlı. Presentation title: Investigation of properties of the new disazodides derived from aminopyrrhizides by DFT method. The new disazodides derived from aminopyrrhizides were optimized by DFT method. The electronic and structural properties of molecules have been investigated by using optimized structures. As a result of the calculation, information were given about the structure and electronic properties of the molecules, such as ionization potential, chemical potential, dipole moment, electron affinity, electronegativity, hardness, softness, and electrophilic. The electronic and structural properties of molecules are calculated by using Gaussian 9 program and Gauss-Weave 5 program using density functional theory with basis set B3 Liang par 6 311 GDP. Keywords: DFT, electronic and structural properties, disazodides. And the outline of the study is as follows. What are azodides? Azodides are a category of dyes that contain azo groups, which are pairs of nitrogen atoms double bonded to each other. Azodides are the largest category of dyes, representing percent 60-70 of all dyes used for industrial purpose. Currently, there are more than 2,000 azodides in the market used to dye cotton, silk, wool, leather, viscose, and other synthetic fibers. They are also used in paints, varnishes, plastic, and rubber. Their widespread use is due to the fact that they are economical and easy to use. Further, azodides also provide stronger and vibrant textile colors. Azodides can be used to color or dye a large class of materials and products, particularly for fabric, leather, and plastic, for which a bright color is required. Azodine materials is widely used in biological and medical studies, computational studies, dye-based solar cells, photochromic materials, metallochromic indicators, sensor, and photosensitizers application. What is the purpose of study? The aim of this study is to investigate the structural, spectroscopic, and electronic properties of newly synthesized disazodides using density functional theory based on a Benizio quantum computing method. Spectroscopic measurements of the newly synthesized samples were carried out in the research laboratory of the Department of Chemistry. Working step: Gaussian 9 package program, a initial calculation method, DFT 3 B3 Liang par, basis set 6 311 GDP, 3A, 3B, and 3C, this is a dice molecules, the three-dimensional shapes, and the equilibrium state geometries of molecules, the determination of electronic properties of molecules by HOMO-LUMO analysis, interpretation of the obtained results. Computational details. The DFT method is very popular method to examine the electronic structural and vibration properties of atoms, molecules, clusters, and solids. Therefore, the molecular structure of these dice molecules in ground state was calculated by using DFT, B3 Liang par methods, and 6311 GDP basis set. The theoretical geometries of molecules which have been optimized are given figure 1. In order to make the theoretical calculation of the synthesized molecules first, the structure were created with the Gaussian view molecular visualization program, and then the structure, spectroscopic and electronic properties of the title molecules were calculated with the Gaussian 9 package software. The structural and electronic properties of the investigated dyes were performed by the DFT 6311 GDP method. In figure 1, the optimized structures of 3A, 3B, and 3C molecules are seen in 3 dimensions. Geometric optimization and structural properties. The approximate geometries of newly synthesized molecules in ground state have been established, and these molecule structures have been optimized by DFT, B3 Liang par 6 311 GDP method. The spatial arrangement and structure of atoms in the molecules with this optimization method were determined. The geometries of these molecules are possessing C1 point group symmetry. These molecules consist of 36, 38, and 40 atoms, and they have 100 to 108 and 114 fundamental vibration modes according to the 3 and -6 role respectively. The structure parameters of the title molecules suggest bond length, bond angle, and dihedral angle, and are given in table 1, table 2, and table 3 respectively. The B3 Liang par 6 311 GDP basis set used in calculation is very useful in calculating the structure properties of dice molecules. The spectroscopic properties of and synthesis of these molecules have been studied in detail in our previous studies. The 3A molecule has 36 atoms, 102 fundamental vibration mode, 13 carbon atoms, 9 nitrogen atoms, 13 hydrogen atoms, and 1 oxygen atom. In table 1, the theoretical bond length, bond angle, and dihedral angle of the 3A molecule are given respectively, as can be seen from table. In the first mode, the bond length between C1 and C2 atoms was theoretically calculated as 1.3950. Likewise, bond angle and dihedral angles were calculated for the 3A molecule. As can be seen from the table in the first mode, the bond angle between C2, C1, and C6 atoms were theoretically calculated as 119.9203. As can be seen from the table in the second mode, the hedral angle between C6, C1, C2, C8 atoms was theoretically calculated. The structural features for the 3B molecule are as follows respectively. The 3B molecule has 38 atoms. In table 2, the theoretical bond length, bond angle, and the hedral angle of the 3A molecule are given respectively, as can be seen from the table in the first mode. The bond length between C1 and C2 was theoretically calculated. Likewise, bond angle and the hedral angle were calculated for the 3B molecule. The structure features for the 3C molecule are as follows respectively. The 3C molecule has 40 atoms. In table 3, the theoretical bond length, bond angle, and the hedral angle of the 3C molecule are given respectively. Electronic properties. According to the quantum mechanics approach, atomic orbitals can be defined as the wave function of electrons. Atomic orbitals can be analyzed with Schrödinger's wave equation solution, but it is very difficult to apply this solution to molecules. The specific approaches are applied to solve this problem. This first is an approximate method known as linear combination of atomic orbitals. The second approach is to determine the chemical reactivity of molecules using external orbitals known as frontier molecular orbitals, the highest occupied molecular orbital, and the lowest unoccupied molecular orbital that have been called frontier molecular orbitals are electron donor and acceptor. HOMO and LUMO are very important in determining the properties of molecules and bond order, shape, and electronic properties of molecular orbitals. In the study, the electronic properties of the molecules investigated were determined with DFT B3 Ley-Yang par 6311 GDP method. The energy levels and distribution of HOMO-LUMO orbitals for 3A, 3B, and 3C molecules are given as an example in figure 2, figure 3, and figure 4 respectively. Then the electronic properties of this dyes, which we call 3A, 3B, 3C, suggest HOMO-LUMO, energy gap, total energies, chemical potential, electronegativity, ionization potential, electron affinity, hardness of molecules, softness of molecules, electrophilic dipole moment have been theoretically investigated. These electronic properties of the molecules are given in table 4. Conclusion: in addition to the experimental values for characterization of these synthesized molecules, the results of DFT-based ab initio calculation are given in detail in our previous study. The geometries of the molecules were optimized by DFT methods, including the 6311 GDP basis set. After the optimization process, the structure properties of the molecules such as bond length, bond angle, and the hedral angle were determined. The electronic properties such as orbital energy, HOMO-LUMO, energy band gap, ionization potential, electronegativity, chemical hardness, and softness were calculated by frontier molecular orbitals. In conclusion, in the study, the DFT B3 Li-Yang par method seems to be a very effective method to examine the structure, spectroscopic, and electronic properties of these dyes. Based on this, we can say that this method can be used in future studies. Thank you.
Thank you, Pınar, for your good presentation.
Thank you.
You have one question. Also, you can write down your question in chat part. The question is, I have a question. There are any experimental data on the structural and electronic properties of these these azodides?
It does apply. Yes. Experimental data on structure and electronic properties of these molecules are not available, but there are spectroscopic and vibration properties experimental data.
Okay, you can plan to any experimental data. Right now, I understand there is no any experimental data, but in the future?
But there are spectroscopic and vibrational properties. NMR, UV, UR, experimental data.
Okay. Is there another question?
Okay.
I think no question. Okay, thank you, Pınar.
Thank you.
The next presenter, Gülgün Mansuroğlu, Berna Çatıkkaş from Mustafa Kemal University. The topics theoretical investigation of electronic and vibrational properties of asymmetric shift base and metal complexes. I think Gülgün has a video. I think we can share his video. Evren, Gülgün, write down me. I have prepared a video. We can share this video.
Thanks, teacher. Now I will give information about my work. A theoretical and investigation of electronic and vibrational properties of asymmetric shift base and metal complexes. Here I will tell you about contents, summary of the study, calculations and result, structure, geometric molecular charge, HOMO, LUMO and chemical properties, total density status, molecular electrostatic potential, contour, consolidation, references, acknowledgements. Summary of the study. In this study, molecular modeling of N2-1-hydroxy-2-acetonoaminobenzyl to carboxyldiamine H2L and its complex with C was performed. The optimized structures of the components were determined and the most stable energy status were determined. For the first time, 3D modeling of these molecules were not theoretical calculations before was theoretically performed. Test calculation and studies will reveal the properties of such molecules and in detail and detailed analysis have taken place in the literature. The method and set of the components studied theoretical and experimental within the scope of the study will be adequate for components with similar structures. Structures, geometric parameters. Geometric parameters aims to find the most stable geometric structure of the molecule. As a result of this calculation, more than one stable structure might occur about the molecule. The main purpose of these calculations to find the most stable. The methods used here are molecular mechanical methods and electronic structures theory methods. Structure geometric parameters. Here are the methods which draw the molecule and the facet. Figure 1. The most stable geometric structures of the molecule. Molecule charge. Here we see the charge distribution of this molecule. Molecular charge is calculated directly based on density matrix, a special reception of electronic wave functions. It's two odds method for calculating atomic charge. Homolumo proportions. All computers have field and empty orbitals calculated. Homo Higgs occupied molecular orbital and LUMO lost unoccupied molecular orbital, which play an important role in the stability of the atom, its electronic properties, and its tendency to enter into chemical reactions. The occupied orbital home is denoted by the empty orbital. LUMO and HOMO has the Higgs energy and tends to don't electrons, while LUMO has the lowest energy and tends to gain electrons. The band gap is the regions between these two orbitals. Figure 5. Homo orbital shapes and energy difference of computers. Cl2 H2O. Figure 6. LUMO and energy difference of computers. Cl2 H2O. Homolumo and chemical properties. This table contains the date notched after the homolumo calculations of the molecule. Chart to chemical properties of compute. Molecular properties electron. Total density status at the end of the calculations obtained is figure related to the total density. The situation was obtained. Molecular electrostatic potential. Molecular electrostatic potential gives information about electronic density. Electron densities differ in hydrogen bonding interactions. In some cases, with electrophilic H-check and nucleophilic properties, molecular electrostatics are used. Figure 8. Electrostatic potential surface map of compound. Contour. The molecular electrostatic potential map is the color-coded map of the coefficient electron density surface. The color scheme for the map in this map is red, electron-rich potential negative charge blue, electron deficient partially positive charge light blue, very few electron deficient region yellow, very few electron-rich region green is natural. Figure 9 electrostatic contour of compound. Conclusions. The method and state of competence examined theoretically and experimentally within the scope of the study have been agreed for competence with similar structures. In the study molecular modeling of and 2 1-hydroxy 2 acetylpropanamino serial to carboxyl H2L2H2O and its complex with C was performance. The optimized structures of the components were determined and the mass stable energy status were determined. Here are the records I used and used while doing his work. Octave comments. The numerical calculations reported in this paper were performed at Tübingen, Ulakbin, peak performance and great competence center Truba resources. This study was supported by the Research Foundation of Mustafa Kemal University. Thank you for attending and listening to me.
Thank you, Gülgün. Is there any question? Actually, I have one question, Gülgün. I'm sorry, I couldn't understand why you investigated these metal complexes. What's your purpose? Which area should be used for this kind of metal complexes? Gülgün, can you hear me? I see the Gülgün name, but I think she doesn't hear me. Okay. Okay, we can pass through the next presenter. The next presenter is Ayşe Uçak, Gülnide Hasdemir, Yasemin Çiftçi, İknur Durkan from Gazi University, and the topics effects of composition on the properties of copper dope, scandium gold, first principle study. Yes. Let's start.
Ayşe Uçak and I'm a student. Dear researchers and students, my name is Ayşe Uçak and I'm a student at the Department of Physics, Gazi University. I'm going to present effects of compositions on the properties of copper dope scandium gold first principles study. I would like to start with outline. First, I will give you some basic information about motivation of the study. Next, I will talk about theoretical background and then I will give the obtained results respectively. I would like to talk about our motivation in this study. Intermetallic rare earth transition metal compounds, B2FAs, have intensively been studied in the last years with regard to their technical importance in physical and mechanical properties. The ability of a material to deform rather than fracture is an essential property in the fabrication and reliable performance of a broad array of metallic components. The scandium compounds calculations of the structural and electronic properties are presented by Mako et al. Their calculations are based on full potential, linearized augmented plane wave method. Moreover, they reported the electronic bond structure in the B1 structure. The electronic properties of B2 type scandium gold compound have been studied experimentally by Palazzo and Marfinetti. They investigated the phase diagram of the selenium gold system within the range 20 to 98% gold using differential thermal analysis, metallographic analysis, X-ray diffraction, and electron microscopy. Copper, silver, and gold are in group 11 of the periodic table. These three metals have one s orbital electron on top of a filled electron shell and are characterized by high ductility and electrical and thermal conductivity. The filled d shells in these elements contribute little to interatomic interactions, which are dominated by the s electrons throughout metallic bonds. So we have decided to perform first principle study to investigate the structural, elastic, and electronic properties of copper-doped scandium gold ternary compounds for an increasing molar fraction of copper atom from 0 to 1 by 0.1. We have applied the virtual crystal approximation to simulate the solid solutions with mixture atom. In this study, we used ab initio methods, first principle studies, density functional theory, Born-Oppenheimer approximation, Hohenberg-Kohn theorems, Kohn-Sham orbitals, and self-consistent field, exchange correlation energy functionals. Here we report a first principles investigation of the copper-doped scandium gold compound based on Kohn-Sham density functional theory. First principles method is based on quantum mechanics, so molecular structure and related properties can be calculated with this method. Solve quantum mechanics Schrödinger equation to obtain eigenvalue and eigenfunction and thus the electronic structure. Calculation methods. CASTEP code is modeling and simulation based on ab initio method. We choose generalized gradient approximation in the scheme of PBE, exchange correlation functional. We choose the cutoff energy of atomic wave functions at 800 eV. Moncourt Peck key paint mesh grid is the edge of 16. Vanderbilt type ultrasonic pseudo-potential electron-ion interaction. The orbitals of scandium, gold, and copper are treated as valence electrons within the crystal approximation. Virtual crystal approximations. In the VCA framework, the atoms in a crystal lattice at the sites with partial occupations by differential chemical elements are represented by the virtual atoms whose atomic numbers, weights, pseudopotentials are taken as the weighted averaged values of the actual atoms sharing the same crystallographic site. In such a way, it is possible to use smaller cells for calculations and significantly reduce calculation time. In the present work, the structural parameters of copper-doped scandium gold B alloys are obtained through structural optimization, in which the different values of doping ratio X of the scandium copper gold alloys are set to be in range from 0 to 1 by using the VCA methods in the B2 structure. Figure 1 shows us unit cell of scandium copper gold. The atomic coordinates of the atoms placed in the unit cell are shown in the table above. And the table 1 shows us calculated lattice parameter, volume, bond length, and formation energy. Negative formation energy indicates that all of the X compositions are structurally stable and synthesizable. The lowest delta H value is at X equals 0.6. Here, you can see the dependence of copper composition on the structural parameters of scandium copper gold. The reason why the lattice constant of copper-doped scandium gold is smaller than that of undoped scandium gold is that the lattice constants are closely related to the radius of the doping atoms, as the radius of copper is smaller than that of gold. The volume increase has the effects of increasing the average gold-scandium bond distance, normally found in either high temperature or stabilized phase of scandium gold. The formation energy for the most stable structure is given in Figure 4. Figure 5 shows us partial density of scandium copper gold X states for X equals 0.6. For scandium copper 0.6 gold, the lowest energy states from minus 16 eV to minus 15 eV are essentially dominated by p orbitals of copper gold compound, while near the Fermi level in conductive bonds, scandium d states is larger. The variation of electron number at Fermi level is another indicator of the structural stability, so the lowest n value can be expected to refer to the most stable structure. According to figures, scandium copper gold achieves the minimum point at x equals 0.6 with a value of n equals 0.98. You can see the elastic parameters formulations in this table. The response of a solid under external forces is determined by the elastic constants. The strength of a solid material can be characterized by calculating the mechanical properties such as bulk, shear, and Young's modulus and Poisson's ratio. To obtain the second-order elastic constants, the stress-strain method is used. Elastic properties are seen for different x values. This copper-doped scandium is mechanically stable. According to the obtained Poisson data, copper-doped gold shows ionic bonding. If the Gb ratio is smaller than 0.5, the material exhibits ductile behavior. Otherwise, it exhibits brittle behavior. Here you can see the elastic properties of scandium copper gold for different copper compositions. These graphs show anisotropy factor and hardness of scandium copper gold for different copper compositions. The results we obtained at the end of this study are as follows. Negative formation energy indicates that all of the X compositions are structurally stable and synthesizable. The lowest delta H value is at X equals 0.6. Lattice parameters, volumes, and bond lengths change with copper composition for scandium copper gold. Scandium copper gold exhibits a metallic behavior. Scandium copper gold is mechanically stable for all copper composition. Scandium copper gold is a soft material. The ionic bonding is dominant for the compound. Its ductile character decreases along with the increasement of the X composition after X equals 0.4. After X 0.5, it has brittle property except X equals 0.9. To the best of our knowledge, most of the studied properties such as structural, elastic, electronic properties are reported for the first time. Thank you for attention.
Thank you for your presentation. Do you have any question? No question. You can write down your question in chat part. Okay, if no question, we can pass through the other presentation. The other presentation presenter is the Berna Atıkaş from Mustafa Kemal University and Nurcan Karacan from Gazi University. The presentation title is Investigation of Vibrational and Electronic Parameters of Antimony Complexes by Using DFT. Berna or Nurcan is here? Or is there any video? Okay, I think. Okay, the video. We can start. But I couldn't see, I couldn't do any voice, hear any voice.
It's okay?
Okay, Berna.
Can you hear my
can
sound?
start.
Yes. Can you see my presentation?
I see, but you can please the presentation mode.
Oh, thank you. Sorry, I adjust.
Okay.
Okay. I adjust my. Can you hear my sound?
I could see your presentation, but yes,
It's okay.
Please write. No, everything is okay right now.
Okay. Hello, a warm hello from Hatay to everyone who listened to me. First of all, it was a beautiful and efficient conference for us and all participants, I think. But it's not seeing me. That's a problem. I didn't do this. This is a technical problem, I think. Why? No, it's not. Okay, thank you. Okay, I continue. Yes, it's a good conference, I said. Therefore, I would like to thanks to Professor Yasemin Çiftçi for devoted effort. And I also thanks my master students for participating this conference. My title is Investigation of Vibrational and Electronic Parameters of Antimony 3 Complexes by using DFT. And my colleague is Nurcan Karacan. In this talk, what am I going to talk about? Firstly, I introduced my molecule's importance, what I am doing this. And then in the second section, I am going to show calculations and outputs. And firstly, in the second section, structure, geometric parameters, frontal molecular orbitals, and the chemical properties, and partial density of states, map of molecular electrostatic potentials, non-linear optical properties of the compounds, and the vibrational studies and scale quantum mechanical calculations, and then conclude. Okay, I'm here. Hello again. Oh. In this study, yes. Okay, I'm here. Daria, I successed my video. Yes, antimony. Why in this study I used antimony 3? Why I am using antimony? Antimony has been used as a drug for more than 100 years. Antimony compounds have also various potential usage in the field of the health and pharmacy, generally, such as antihelmintic and antithyroponosomol and antimicrobial, antifungal, and anti-cancer agents, and for the treatment. And antimony complexes with new shift bases containing carboxamide groups. Firstly, I will show the 3D two-dimensional molecule, and then the number 2 and the number 3 one is here. These molecules are new shift base, and carboxamide groups these have. And although this is the importance is the sentence. Although the different theoretical calculations on the antimonetary complexes have been performed, only the few reports on the vibrational analysis of the antimony compounds are found in the literature. That's why I'm studying this. And antimony complex with the shift-based ligands determined by optimizing geometric structures 1, 2, and 3, number of the compounds. The long name of the numbered complexes are shown in the table. This is the table, the long name, and the complete vibrational assemblies and the simulated IR spectrums of the fundamentals were constructed with the help of the density functional theory and the scaled quantum mechanical force field procedure. Wide vibrational calculations, calculated and experimental IR spectrum show that the all-inclusive picture on the electronic position and the correct structure information about the studied molecule. And now it's the second sections, results discussion section. Structures, geometric parameters for the optimized structure of compound 1. Number 1, the bond length and the antimony charge for the compounds is in the table. And now I'm going to information about the geometric parameters of each molecule respectively. And this is the molecular chart here. And molecular structures calculated using by B3L, IPL, and L2DZ. And the number 2 is here, and the number 3 is here also. I did this calculations and the tables, and then the next one is frontier molecular orbital. Yani and means the homolumo energies of the 3 molecules are plotted together in the figure 4, and the chemical properties of the 3 complexes are tabulated in the table 4. Here, and then the partial density states diagram as shown in figure 5. To quantify the contributions of the moieties to frontier molecular orbitals, the total and partial density of states have been calculated using by Gaussian program, which has been partitioned of about the 3 different groups, about antimony and ring and the others contribution percentage. I'm going to show this part. And if we look at the molecular orbitals, the molecular orbital density on each molecule, you can see the green circles, and look, and while the HOMO 98% of the number 1 complex around the antimony atom, it's seen that on the other atoms for number 2 and 3 is different. And the LUMO molecular orbitals we can look. Also, the LUMO molecular orbital about the number 1 ring around the ring number 1, while the number 2 and 3 is around the ring contribution mostly. And then the molecular electrostatic potential map now, and we can look the rich electron region and the poor electron region we can see, and number 1, 2, and 3 molecules, and vibrational studies here. The section vibrational studies, it's a complicated, of course, but I simplified some. For example, carboxamide vibrations, carbon and oxygen vibrations region is here, and the carbon, nitrogen here, and the antibond color for the complex, this is the par region, and the number 2 is the different for the S atom, new S atom here, and the S sulfur atom vibrations region about these vibrations, and number 3 vibrations also here you can see, and how many times I have? Okay, and for the number 3 vibrations, we can look the IR spectrum, and also calculation IR spectrum below, and the non-linear optical properties of the compounds section here, and the polarizability, first order hyperbolarizability, and their relative component values of the title compounds, and urea were given in the table. Urea is one of the phototypical molecules used in the study of the NLO properties, NLO properties of the molecular system, and therefore it was used frequently as the threshold value for the comparative purpose. And the value beta total for number 3 compound is about the 25 times larger than the urea. In addition, the value of the beta total and beta urea found, the other one is here, the less than the number 3 for the complex. And then the conclude, in this study, the density functional theory DFT calculations studied were carried out to support the chemical findings. The most stable conformers have been found for compounds 1, 2, and 3 number. Optimized molecular structures, frontier molecular orbital properties, map of the molecular elastic potentials, and the non-linear optical effects of the molecules tabulated and reported. The theoretical studies on utilized B3LIP density functional method with ln L2DZ basis set were determined by using Gaussian 9th of Baire package, and the SQM result is also here, and then here is my reference and the acknowledgements. I would like to thank you, the Turbo Resources and the Research Foundation of Hatay Mustafa Kemal University, and thank you for the listening me and time. Kindly regards.
Thank you, Berna, for your presentation. Pınar asked a question. I'm read her question. Are there any experimental consequences of the structural parameters of the molecules?
Not now. I haven't now. That's why it's not here.
And continue. If yes, were the measurements taken with XRD?
I don't think so. I don't want to. Exactly. Okay.
I also want
Thank you for the question, Pınar.
I'm wondering, I'm sorry, I'm not expert on these topics. I'm just wondering, what's the difference? Tell me, the DFT and the scale quantum mechanics. Why do you need?
It's very different.
Why do you need, except from the scale quantum mechanic?
Okay, it's a good question, actually. It's DFT calculation, it's the harmonic calculation. That's why the vibrations is not correct. Therefore, we use the correction that we can scale parameters. We can use the experiment. Firstly, experimental data we used for the scale, and also we need the scale. That's why the be using physical procedure.
Thank you.
Do you see?
It's okay. Thank you.
Okay. Also, Gülgün question I want to answer. Your answer, Gülgün, is not here. Yours questions.
Okay.
She's sorry.
I
She's sorry
forget
about
my
that to me.
question.
And
I forget my question.
oh, okay, it's no problem.
Just
Okay, thank you. Bye.
continue. Okay.
Any question? Are there any?
I think right now there is no any question. Okay. See you, Berna.
Bye bye.
And next presenter is İnanç Yılmaz, Ülkü Bayhan from Mehmet Akif Ersoy University. And the presentation title is The Structural, Elastic, Electronic, Vibrational, Optical and Gravimetric Hydrogen Storage Capacity, Properties of the DFT Study. İnanç or Ülkü? Yes, okay.
I'm here.
Okay, we can start.
Hi all. I'm İnanç Yılmaz. I am a PhD student in Burdur Mehmet Akif Ersoy University. My presentation title is The Structural, Elastic, Electronic, and Vibrational and Optical Properties, Optical and Gravimetric Capacity Properties of the wait a minute. Perovskite type hydrides. It's a DFT study. There is my outline, motivation, calculation methods, physical properties of perovskite type hydrides, such as structural properties, elastic properties, electronic properties, vibrational properties, and a conclusion. My motivation is, as you know, greenhouse effects is dramatically bad, and high consumption, air pollution, negative effects on human health, and environmental effects. Fossil fuel resources are decreasing day by day at an increasing rate. Due to such many reasons, the search for sustainable and renewable energy resources is seen as an issue that increases its importance exponentially. Perovskite type hydrides such as AbO3 on literature, but approximation is perovskite type hydrides. It's AbH3. In figure B, represent of rubidium X H3, X equal to beryllium, calcium, and magnesium. Important properties, they in view important properties in view. Pardon. Hydrogen is considered to be an ideal fuel source instead of traditional energy resources due to its cleanness and abundance in the universe. Hydrogen has a high ratio of energy per unit mass and can provide electricity at affordable prices. Particularly, hydrogen storage is an open question for researchers. As you know, some metals can store hydrogen in the solid form, known as metal hydrides. This procedure of storage of hydrogen is known to be safer and possesses higher density compared to both cryogenic liquid and pressurized gas methods. There is my calculation methods. Can you see me? Oh,
We can see you. There's no problem.
okay. There is my calculation methods. Rubidium XXH3 compounds were performed and their rubidium XH3 compounds and their unique properties were performed via an ab initio simulation package. These are I was chosen pistopotential Paderburg Enzerhof K points sham gamma centered on 16 times 16 times 16 cutoff energy 700 electron volts exchange correlation my exchange correlation energy generalized gradient approximation. Physical properties, structural properties, elastic properties, anisotropic elastic properties, electronic properties, that's dynamical properties. These are structural properties of rubidium XH3 compounds. Since delta HF, they are mechanical, stable, and size-stable. Delta HF is using equation 1. Elastic properties elastic properties represent in table 2 H new parameter is 3 options Vickers hardness. In table 2 represent values. These equations use these equations. In table 3 B divided by G ratio, G divided by B ratio, VL, VT, VM, wave velocity, Debye temperature, gravimetric hydrogen capacity represented in table 3. In table 3 values was calculated these equations. Using these equations, in figure 2, rubidium, beryllium H3 bond structure and corresponding density of states, there was semiconductor behavior. Rubidium, beryllium H3 has an indirect band gap. Band gap value is 0.274 electron volts. Figure 3 represent a rubidium calcium H3 bond structure and current bonding density of states. That is it's rubidium calcium H3 compound has a direct band gap. Band gap value is 3.264 electron volts and conducting mainly D bands. In figure 3, bond structure and corresponding tensor of states of rubidium magnesium H3. Same as rubidium calcium H3, but there is a not mainly same. Rubidium magnesium H3 has a indirect band gap with 2.209 electron volts. Vibrational properties, it's DFPT calculation, 2 times 2 times 2 supercell, same as again 10 times 10 times 10 gamma centered K point. In figure 5, phonon dispersion curves and corresponding tensor of states rubidium beryllium H3. As you see in figure 5, there was a negative mode due to not stable for in question compound. Phonon dispersion in figure 6, phonon dispersion curves and corresponding tensor of states rubidium calcium H3, sorry. And the in figure 8, the thermal properties of rubidium calcium H3. Rubidium calcium H3 compound has stable because there is no negative mode. In figure 8, phonon dispersion curves and corresponding tensor of states rubidium magnesium H3, and figure 9, the thermal properties of rubidium magnesium H3, same as rubidium calcium H3. There is no soft mode due to its stable. Conclusion: our compounds was found to be mechanically stable and synthesizable. The increased lattice constants leads to a decrease in the bulk modulus, which our compounds was agreed that theory. Position ratio give information of nature of bond to us. That value usually around the 0.1 for covalently bonded materials. Our results has calculated position ratio around 0.1, so compounds are covalently bonded materials. Rubidium H3 compounds are brittle since B divided by B divided G ratio is below 1.75. This is thought to confirm about the knob hardness. The perovskite type hydrides, rubidium beryllium H3 and rubidium magnesium H3 has indirect band gap of 274 electron volts and 2.209 electron volts, while rubidium calcium H3 has direct band gap of 3.274 electron volts respectively, and therefore these compounds has shown semiconductor behavior at equilibrium. It can be said to be rubidium calcium H3 and rubidium beryllium H3 was stable compounds according to the phonon calculation about these compounds. There's my references. Thank you for your attention.
Thank you, Inanç, for your presentation. Do you have any question? I have one question, Inanç.
Okay.
You told that this kind of materials should use in hydrogen storage materials, but I couldn't see any investigation in theoretical investigation towards hydrogen storage properties. You investigate some mechanical and elastic properties, but I couldn't see any towards the hydrogen storage properties of this kind of materials.
My compounds, hydrogen storage, my compounds calculated gravimetric hydrogen storage gravimetric hydrogen storage capacity in table 3, the last one. So
how to determine this value? This is theoretical value, I think.
Yeah, theoretical value.
But not investigate this as a theoretical approach.
I investigate. There is a 14 equation. 14 equation. But there is no matched on the literature. So beryllium compounds has a hazardous due to not experimental studies on literature, but rubidium calcium H3 and rubidium magnesium H.
I'm asking the binding energy, binding absorption energy, not this. I know this formula. This is like the theoretical hydrogen storage capacity show us. Okay. Some absorption energy.
Absorption energy, I'm not calculated.
Okay.
So octahedral hydrogen structure is not stable on in my approximation. So binding energy or approximately binding energy and absorption energy I have not calculated.
Okay, maybe next time you can calculate this kind of energies.
Thank you.
Find some experimental data. I know in the literature, I am studying the experimental with hydrogen storage materials. I know this kind of materials is very good materials. So I know maybe next time you can compare the experimental values.
Yeah,
okay.
Yeah.
Thank you.
Well,
I couldn't see another question. We pass the next question. Next presentation. The next presenter is Ozan Bozoğlu, Meltem Baran, Yasemin Çiftçi, İknur Durukan from Gazi University. And the presentation title is a first principle study of pressure-induced effects of phase transition, elastic, electronic, and vibrational properties of a terbium sulfide compound. Ozan, Meltem, see, okay.
My name is İlknur Durukan. I'm working at Gazi University. My presentation subject is a first principle study of pressure-induced effects on phase transition, elastic, electronic, and vibrational properties of yttrium-sulfur compound. This is my outline. First, motivation, calculation method, structural properties, phase transition, elastic properties, electronic and vibrational properties, and finally, conclusion. Motivation. Rare earth compounds attract considerable attention due to the intricate electronic properties relating to the highly correlated F electrons. Pressure is one of the external parameters by which the interplay of the F electrons with the normal conduction electrons may be varied. The rare earth monopnictides and monochalcogenides are some of the structurally simplest materials, and numerous experimental works have studied the pressure behavior of these compounds. In recent studies, high-pressure structural behavior of binary EB compounds with sodium chloride type structure have been a popular topic in condensed matter research. These rare earth elements are trivalent, and their corresponding monopnictide compounds show the lanthanide contraction, and these compounds show metallic character. The yttrium pnictides crystallize in sodium chloride B1 structure. High pressure is an important physical variable affecting the property of the materials as well as the chemical properties of materials. When a material is compressed, it is generally deformed. This deformation behavior helps to understand the nature of solid-state theories. These compounds undergo the first structural phase transition from sodium chloride B1 structure to cesium chloride B2 structure at high pressure. Therefore, in the present work, we have performed a more detailed discussion on structural, mechanical, electronic, and vibrational properties of yttrium sulfur both in B1 and B2 structures, including pressure effects. Conclusion methods. We use CASTEP codes, modeling and simulation based on EB ab initio methods. GGA-BPE for the exchange correlation functional. The energy cutoff for the plane wave basis sets 700 eV. Mork and Peck grid of key points 14 cross 14 cross 14. Structural properties. Yttrium sulfur, figure 1, unit cell of yttrium sulfur E B1 structure. Yes, this is yttrium sulfur. This one yttrium and this one sulfur. Table 1 atomic coordinates. Space group no 235 25 FM3M. Fast transition. It can be seen clearly from figure 2 that B1 structure is more stable than B2. Yes, B1 and B2, B1 more stable and B2. We use calculated these parameters and a lattice parameter and this one volume and total energy. We calculated B1 and B2 and you can see fast transition. Yes, figure 3 estimation of phase transition pressure from B1 to B2 structures for yttrium sulfur. The relative stability of the two crystal structures corresponds to the lowest Gibbs free energy given by this equation. Here, U is the total internal energy, P is the pressure, yes, P is the pressure, T is the temperature, and S is the entropy, and V is the volume. Yes, V is the volume. Since we have optimized structural parameters for both phases at 0 Kelvin, the Gibbs free energy becomes equal to the enthalpy. Therefore, this transition pressure is specified by calculating Gibbs free energy at 0 Kelvin. The related enthalpy change versus pressure graphs are plotted for both phases in figure 3, where crossing point of each P curves is the transition pressure. Yes, about at 3.6 gigapascal, 3.6 gigapascal between structures. Yes, fast transition pressures is 3.6 gigapascal. Fast transition. The volume changes incorporated with various pressure values for both structures are drawn in figure 1. It can be seen from figure 4 that decreases with pressure. With the increase of pressure, the relative compression of the structure is decreased due to the repulsive interaction among atoms. From the graph, one can estimate that the volume collapse percentage value at the point of the fast transition is 8.6%. Calculated transition pressure and volume collapse. Yes. Pressure and volume. Elastic properties. By using elastic constants, it is possible to understand how materials react to any pressure change, such as changes in reasonable distance in symmetry, which affects the overlaps, bandwidths, the hybridization, and bond repulsion. In this study, the second-order elastic constants of yttrium sulfur for B1 and B2 structures are calculated at 0 gigapascal by using the stress-strain methods. Also, second-order elastic constants combinations such as Paschen value, Young modulus, yes, Young modulus, isotropic shear modulus, and Pag ratio, GB ratios under 0 gigapascal are obtained and given table 4. B phase is mechanical stability, but B2 not mechanical stable. Electronic properties. The energy, bond structure, and total density of states of yttrium sulfur at 0 gigapascal for B1 and B2 structures are present in figure 5 by setting the Fermi level at 0 electrovolts. Our results show that B1 and B2 structures of yttrium sulfur have metallic nature due to multiple valences and conduction bonds crossing each other on the Fermi level. The total and partial density of states could give more details about the electronic properties of atoms and orbitals. To clear up the bonding properties of yttrium sulfur, the total and the partial density of states are given in figure 6 by energy range change from minus 15 electrovolt up to 10 electrovolt. As seen in figure 6, the total dose value of B1 of the Fermi level is lower than that of B2, indicating more stable of B1 than B2. According to P-dose curves, partial dose curves, while SP and SS states, SS and SP states dominate the valence bands in B1. Lower energy of the valence bands Moreover, there is a pseudo below the Fermi level due to strong hybridization between yttrium and sulfur in B1 structure. Pointing out metallic conductivity of B1 structure, for both structure near the Fermi level, F states of yttrium is dominates. Yes, F states is dominant, B1 and B2. Vibrational properties. For the high symmetry direction in the beryllium zone with a 2 cross 2 cross 2 cubic supercell, our calculated phonon dispersion and phonon dose curves are given in figure 6. Since there is a big mass between yttrium and sulfur atoms, there is an evident band gap between acoustic and optic bands for B structure. Since there is no negative frequency in the phonon dispersion curves for B structure, it can be concluded the dynamical stability of yttrium sulfur in B2 structure. Yes, this is our conclusion. In summary, the first principle calculations have been performed to investigate the structural, electronic, elastic, and vibrational properties of yttrium-sulfur compound. The predicted value of phase transition pressure from B1 to B2 structure is 3.6 gigapascal and volume collapse 8.6%. The obtained lattice parameter of B1 structure is in good agreement with experimental data. Our results for the elastic constant satisfy the traditional mechanical stability condition. Negative Cauchy pressure in B1 structure implies that the non-central forces are dominant in the bonding mechanism. The computed bond structures exhibit metallic character. Finally, the obtained phonon dispersion curves show that this material is dynamically stable. Thank you very much.
Thank you, İlknur, for your good presentation. Is there any question? Do you have any question? No question. If no question, we can pass the next presentation. I'm not sure the next presenter is here. I'm asking Emine Güner, Fatma Göde, or Nilgün Ozpozan is here. I think no. If no, we are passing this presentation, and at this point, we finished the oral presentation and passing through the poster presentation. The first poster presentation is given by the Eileen Aytaç, and the topics is platinum tin oxide carbon composite as cathode catalyzed support for high temperature polymer electrode membrane fuel cell.
Hi.
Hi.
Hi, everybody. Hi, Derya. Okay, I think earlier to take me here, but no problem. If you share my poster, I can start as soon as possible. Or
Okay.
should I? Okay, maybe should I share by myself? 1 minute, please.
If you send your presentation, maybe everyone
1 minute, 1 minute, no problem.
Okay.
I will share it. Share it. Okay, here, no problem. Sorry. Okay, that's all.
Okay.
Do you get it?
Yes, we get it.
Hi again. Today can you see my poster?
Just this, I'm not sure your poster. I think not. Yes, right now it's okay. There's no problem.
Because-
We can see it.
But the problem is I can't see my poster, so how can I talk about it?
Maybe.
Okay, I think it's okay now.
Mhm.
Okay, thank you very much, Daria. Sorry. Hi, dear participants. Now I would like to give some very short information about our high temperature PEM fuel cell study titled tin oxide carbon composite supported platinum as a cathode catalyst for high temperature polymer electrolyte membrane fuel cell. As you know, some of you, high temperature PEM fuel cell have some advantages. For example, high tolerance to the carbon monoxide, no humidification necessary, simple water management, compact cooling system, possible usage of the waste heat. One of the major problem is the electrode materials degradation in the low pH and the high temperature environment. The continuous degradation of the fuel cell performance is mainly attributed to carbon-supported corrosion and the degradation of the catalytic metals. This was the main motivation for me because this study is supported from Forschungszentrum Jülich in Germany and also TÜBİTAK. Okay, if I mention about my study, nano-tin oxide activated carbon catalyst supported has been synthesized by electrolysis deposition method for high temperature fuel cell. The catalysts of varying platinum contents were characterized by using XRD, SEM and EDX. Nano-tin oxide activated carbons supported platinum as a cathode catalyst was investigated by cyclic voltammetry, electrochemical properties evaluated by cyclic voltammetry coupled with a rotating disk electrode showed improvement with the tin oxide addition. The synthesized catalyst performance was as good as the performance of the control commercial catalyst. High temperature polymer electrolyte fuel cell measurements performed at 160 degrees centigrade under dry gases, hydrogen and oxygen, showed 0.88 volt at the current density of 150 milliampere per centimeter square. When the catalytic catalyst contained a higher concentration of tin oxide, the performance decreased as a result of the mass transport limitation within the electrode. Durability tests showed that tin oxide carbon supported platinum catalysts prepared in this work were stable under the fuel cell working conditions during 350 hours at 160 degrees centigrade, demonstrate as a potential cathode catalyst for high temperature PEM fuel cell. Nano-tin oxide nanoparticles with a high surface area were successfully prepared as a promising cathode catalyst support for high temperature PEM fuel cell. although the oxide materials are considered as alternative support to overcome the carbon corrosion problem in this type fuel cell, the intrinsic semiconductor properties are the hardly to apply them to actual electrocatalyst support. But platinum, this catalyst, tin oxide and carbon supported platinum catalyst, show good electrochemical activity for oxidation reduction reaction in cyclic voltammetric analysis, both sulfuric acid and phosphoric acid. Thank you.
Thank you, Eileen. Is there any question? Yes, one question from Razali.
Yes.
I'm reading the question. May I know the surface area of the nano tin oxide catalyst? The surface area, asking the surface area of your catalyst.
For tin oxide.
Nano tin oxide, yes.
And the particle size is around 18 nanometer.
The surface area, asking the surface area.
But I don't know the surface area because it was not necessary for us. But if he asked to me about the surface area of a specific surface area.
Yes, you can write down in the poster the nano tin oxide particles with high surface area. I think the Razali wondered these numbers.
Okay, but the content of tin oxide was changing. So I just give some information about the amount of tin oxide. But now I don't have here in this computer. If he write me as an email, I can reply. Okay. No problem.
I didn't have also one question. I am wondering the electrochemical measurement. You did some experiments. I'm wondering over potential and the TOEFL slope. Do you have this value? Its value? Well, I'm wondering especially TOEFL value.
I didn't put here the results of the TOEFL corrosion potential and current density results because first I should ask the Yuli. Yes, something is under control, and that's why I give some short explanation here. When I take the
manuscript.
Okay.
Maybe we can read your manuscript.
Then I will send. Okay, but we can share each other later, no problem.
Okay, thank you.
I have all this data. I think second presentation.
Okay,
also
I think the next presentation is also you again.
Yeah. And now I.
Okay, we can press the other presentation.
Yes, I know. And technical stuff will be shared by videos.
Technical stuff said me. You share.
No, it's here. Okay. Hi, dear participants. Now I would like to give the brief information about our materials.
But Eileen, your punto is very low. I couldn't see this
based composite propellant. The aim of our work is to understand.
It's okay here.
Environments such as humidity and oxygen on composite propellants during aging. Motor case is exposed to the different environmental conditions such as oxygen and humidity during its storage. Aging starts from the surface of the propellant in the motor case. The aging trends are determined by environmental conditions and their effects. The oxidative cross-linking of the polymer binder is the main degradation mechanism over time for samples stored under air during the aging. In the presence of oxygen peroxide, contaminants leads to different reactions. Carbonyl and the acid formation cross-link through the various mechanisms. The formation of this functional group causes an increase or decreases cross-link density, which affect the aging characters of the propellant. And the humidity plays an important role, like oxygen on the aging of the propellants. In this study, first we prepared the composite sample, and inert composite sample were prepared at different hydroxyl terminated polybutadiene, HTPB, and aluminum ratio. Then samples were aged at 19 degrees centigrade for the 22 days in the conventional oven under humidity and the oxygen atmosphere. The corrosion behavior of the composite materials were investigated by using TEFL extrapolation method, and the microstructure was investigated, XRD analysis. If you look at XRD analysis, or first you can look at the table 1. Composition of the sample are given table 1. The ratio of hydroxyl terminated polybutadiene and aluminum was changed, while the amount of other ingredients were constant. As you see in table 1, we were used potassium chloride as a solid filter, toluene isocyanate, TDI as a current agent, and the deoxyl adipate as a plasticizer, and some antioxidant like AO. All samples were cured at 60 degrees centigrade for a week. Yes, you can see table 2. And we used the Arrhenius equation. Arrhenius equation has been used to predict the behavior of the materials in the shortened times with the accelerated aging instead of the natural aging for a long time. Then we were aged the sample at 90 degrees centigrade for the 22 days in oven under 75% relative humidity. The sample were taken out from the oven at 2nd, 7th, 11th, and 22nd days, then analyzed. Yes. If you look at the table 3 and also, yes, table 3. Okay. First figure 1 shows the X-ray, X-ray diffraction results of the unaged and unaged and the aged samples after several years. Also, table 3 gives the peak intensity and 2 theta degree related with structure of aluminum. As you see in table 3, there is a thin film layer formed, aluminum oxide, aluminum hydroxide, aluminum oxyhydroxide on the surface of the unaged sample at the beginning. After the 1 year aging, while peak intensity aluminum hydroxide decreasing, intensity of the aluminum oxide increased. After 3 years aging, there is an incredible increasing of the metallic aluminum. After 5 years aging time, formation of aluminum oxide increases. Aluminum hydroxide and aluminum oxyhydroxide, gamma alumina or alpha alumina can be formed at the surface of the aluminum. Aluminum oxyhydroxide can react with the underlying aluminum which produce hydrogen bubbles. If you look at the electrochemical measurement, yeah, here we have 1, 2, 3, 4, 5 TFL plots here. The electrochemical parameters such as corrosion potential and the corrosion current density obtained from the TFL polarization curves and corresponding aging time are given table 4. From the data, there is an increase of the corrosion current density with aluminum ratio in the sample for unaged sample, except for the sample 3. Corrosion current density decreases after first year for all the samples. On the other hand, you can see an incredible increase at the corrosion potential and the corrosion current density after 5 years aging. This can be caused by consumption of antioxidant, plasticizer depletion, decomposition of the oxide layer, structural problems due to the thermal phase transfer, and formation of the microcavities. When the sample after the 5 years and the 10 years are compared with each other, again current density decreases. It is obvious to see current density has a tendency to change with the aging time, but there is not any relationship between corrosion potential and the other variables. So based on the TFL extrapolation curves and the microstructural analysis, we can say there was a tin oxide layer as aluminum oxide, hydroxide, oxyhydroxide formed naturally on the surface of the unaged sample. So the surface was passive at the beginning. There were some transition reaction between all this kind of oxide form on the surface. After 1 and 3 years, these forms were determined by XRD analysis. Due to the oxide layer, the surface was still passive. After 10 years, again, oxide layer as aluminum oxyhydroxide form, and the surface became passive. Active passive transitions on the surface followed each other during the aging. It was revealed that the results obtained from the XRD analysis and the electrochemical measurements are compatible with each other. Thank you very much.
Eileen, thank you, but I couldn't see anything. I think we couldn't understand your presentation.
Why?
I couldn't see anything, any table, any figures. The punto is very small, and I think.
But in my screen, in my screen, it's okay. Why is changing like that? In my screen, it's very well.
You can share, and maybe you can open your poster again. In this version, we couldn't see anything.
Maybe you didn't close your screen. That's why, because I see your face.
I think everybody couldn't see anything.
I don't know. Okay.
We see, okay. but everything is so small.
I didn't share it. Technical support is shared. Okay. I sent the videos. Okay. Thank you. Is there any question?
I think no question because we couldn't understand your presentation. Sorry about that.
No problem. Thank you, Derya. Thank you.
Thank you, Eileen. The next presenter is Fadime Irmak Balmumcu, Ziya Merdan from Gazi University. And the topics analysis of structural, electronic, and magnetic properties of palladium-based alloys. Fadime, is here. Or is there any presentation? Yes. Irmak, I couldn't come hear your voice. Please open your voice.
Okay. Can you hear me?
Yes.
Thank you.
And then again your presentation, we couldn't see. Please make the bigger. And maybe you change the presentation mode.
I sent before a video.
Okay. Maybe the technical part is open your video. But
I try it, but it.
Yes, the last one. The last one. Is this your video? I couldn't understand. Your video starts?
Yes, but
I'm not come hear any voice. Maybe you can summarize.
I try share it. Okay. Hello, my name is Irmak Balmuncu. Welcome to my presentation. Today I will talk about hostile compounds and analysis of the structural, electronic, and magnetic properties of palladium-2 iron thallium compounds. In this study, structural, electronic, and magnetic properties of this compound were examined. Calculations were made using the WASP package program based on density functional theory and generalized gradient approach. Firstly, I will talk about Hessel compounds. The Hessel compounds were discovered first by Friedrich Hessel at 1903. There is two types of Hessel compounds, which are called half Hessel and full Hessel compound, which are given XYZ and X2YZ general formulas. The full Hessel compounds are X2YZ chemical formulas and in which X and Y are transition metals and Z is the main group element. The most important feature of first-type compounds is that the ferromagnetic properties can change when the elements that make up the compounds come together. These compounds, which have ferromagnetic properties, show metal or stereometric properties, having an important place in spintronic and thermodynamic application. Figure 1 shows that the schematic representation palladium-2 iron thallium compounds. Now I will talk about material and methods. Calculation with the scope of the study were made using the generalized gradient approach. The structural and magnetic properties of the palladium-based palladium-2 iron thallium compound were first studied by means of the WASP program using principal methods. For the primary base set using in the expansion of wave function, the shape energy value was determined as 500 electron volts. The lattice parameter, magnetic moment, and bulk model values of this compound are given table 1. There is one study to compare lattice parameter and magnetic moment value. In the thesis is written by Gaston, only lattice constant and magnetic moment are calculated. The obtained result shows that these values are highly compatible with the reference data. In a study, bond structure and density of state graphs for palladium-2 iron thallium compound were obtained and analyzed. Figure 2 shows the the bond structure of this compound. There is no band gap between the energy bands for this compound, and the compound has a metallic structure. In addition, for better analysis of the electronic configuration, the total and particle density steric curves according to spin orientations are shown in Figure 3 and Figure 4. According to Figure 3 and Figure 4, do not contain a band gap around the Fermi level, and palladium to iron thallium compound shows a metallic character. In this study, the structural and magnetic properties of this compound with the density functional theory. The lattice parameter is 6.360 angstrom, and magnetic moment is 3.063 Bohr magneton per formula unit respectively. One structure and density of state graphs have been obtained and shows metallic properties of this compound. As a result, due to the properties shown by this compound, it can be said that it may be any possible material for use in spintronic and magnetoelectronic device. Thank you.
Irmak, thank you. But again, we couldn't see anything. The text is so small, if you realize that.
Thank you.
Okay. I'm saying that, but maybe the week you can attend the next presentation. Be careful about that. We couldn't see anything.
Okay.
Is there any question? No question. I think the next presenter is also you. Am I right? Okay, you can open your next presentation.
Hello, my name is Irmak Banlamir. Welcome to my presentation. Today I will talk about Hessel compound and the first principle calculation of cubic structure of palladium to manganese bismuth. In this study, calculation of electronic, magnetic, elastic, and structural properties of this compound. Calculations within the scope of the study were made using the WASP-Pascal program. The calculations were performed using density functional theory within the generalized gradient approximation. Firstly, I will talk about material and method. Calculations within the scope of the study were made using the WASP-Pascal program. Perder-Berg and Zerhoff generalized gradient approach was used for exchange correlation energy. The kinetic energy share value of plane wave is 500 electron volts. Elastic constants were calculated using WASP program, keeping all parameters constant. In this study, the equilibrium lattice constant is determined by minimizing the total energy corresponding to the different values of the volume and shown in Figure 1. The value corresponding to the minimum energy from this chart gives us the numerical value of the meshed constant. Table 1 shows that the lattice constant, total magnetic moment, and bulk model for this compound. The total spin magnetic moment and lattice parameters of palladium to manganese bismuth compound were obtained 4.457 Bohr magneton on per formula unit and 6.485 angstrom respectively for this compound. In the thesis written by Gilson, only lattice constant and magnetic moment are calculated. As a result, the resulting lattice constant and magnetic moment value are hardly compatible with the available data. Table 2 shows that the calculated elastic constant, share modulus, E divided T ratio, Young modulus, and Poisson ratio. Direction of the crystal against an external strain are given by flexibility calculation. The bond stability criteria of cubic crystal for cubic structure, the elastic stability combination having the below equation. When they are analyzed, the calculated elastic constant do not provide the bond stability principle, and it is observed that the palladium to manganese bismuth compound is not mechanically stable. Spin polarized bond structure of this compound along high symmetry direction in the first previous zone are shown in figure 2. As can be seen, there is no electronic bond right for both spin up and spin down at Fermi level. When the dose graphs for this compound are examined, it appears that there is no energy range and polarized bond structure for spin up and spin down states exhibit metallic character. As a result, studies were conducted within the framework of DFT with the generalized gradient approximation to analyze the structure and electronic properties of palladium-2 manganese bismuth compound in the present research. The lattice constants and total magnetic volume were compared with the data available, and they are compatible with each other. The bond structure and those graphs for palladium to manganese bismuth compound were analyzed, and this compound exhibits metallic character. Moreover, it was observed that its calculated elastic constants do not provide the bond stability criteria, and the compound palladium to manganese bismuth is not mechanically stable. Thank you for attention and listening my presentation. Thank you.
Thank you, Irmak, again. Do you have any question? Okay, no question.
Thank you.
Thank you. The next presentation, the presenter is Osman Yağız Aktuman and Ali Murat Soydan from the Gebze Technical University. And the topics, the fabrication and characterization of microtubular solid oxide fuel cell with yttrium stabilized zirconia and half-Nia Erbia co-doped bismuth oxide bilayer electrode. Osman Yağız is here.
Hi.
Okay.
Yeah, I'm here.
Can you share your presentation?
Sure. Yep. Can you see it?
Yes, we see it.
So can you read the data? Because
Okay.
it's a problem today, I guess. I would like to start with welcoming you all. And today I'll talk about our study, fabrication and characterization of microtubular solid oxide fuel cells with bilayer electrolytes. In the study, we developed or synthesized an electrolyte material called Hafnia Erbia co-doped bismuth oxide, which is a high oxygen conductor, oxygen ion conductor. We used oxide version of Erbia bismuth oxide and Hafnia powders to synthesize the HAV powder, in short. We used standard mixing in a polyethylene jar in a ethanol media, and after that we dried this and calcined some part of the powder and then pressed into pellets the other part of the powder, and we furnaced and fired them at 750 Celsius. And then we wanted to see if we have the correct phase. So we analyzed the powders and the pellet form samples by XRD, X-ray diffraction method. And then it was successful. I'm not sure if you could see from the diffraction data over there. And we continue to produce cells after we successfully synthesized the HAV powder. First, we extrude anode supports in tubular shape, then coat it with YSC electrolytes, and then fired them, co-sintered the samples. And you can see the micrograph also on the central block of the figures. On the second one, just below the XRD results. And then we coated HAV layer via deep coating also. You're seeing the yellow layer on the tube. It is unsintered because I couldn't share the sintered one because when we sinter it, it's so thin and it's transparent. So we cannot see if there is a layer in there from this picture. And then we coated the cathode and measured. I forgot to mention, we also used electroimpedance spectroscopy for the pellet forms to see how good the material conducts the ions. And at 600 Celsius, it reaches 0.114 Siemens per centimeter. It is pretty good in terms of ionic conductivity. Considering the YSC has a conductivity at this temperature 0.006, so it's pretty high compared to YSC material. And we also tested our cells with bilayer and single layer electrolytes. As you can see, blue lines shows for the shows the results for the double layer electrolyte cell, and the red one is for YSC single electrolyte. So the peak power density at 600 Celsius is almost 1 watt per centimeter squared, which is pretty impressive for a tubular cell, and the YSC cell showed only 0.51. The main reason behind this, the HAB electrolyte, basically the bismuth type electrolytes, has surface exchange rates are better than most of the material we know, and this accelerates the ionic conductivity, and cells gave better performance compared to the others. Thank you. That's all from my side. If you have any questions.
Thank you, Yağız. Actually, do you have any question? No question. I have one question.
Sure.
I'm wondering the role of the Hafnia-Erbiye on your results. I'm wondering. I'm not know this Hafnia-Erbiye, these compounds or bacteria.
No, it's ceramic actually. Hafnia is a term for hafnium oxide, and Erbiye is erbium oxide. So they're just ceramic materials, oxide materials. I'm not sure if I could.
The role of on your result of this Hafnia-Erbiye.
Oh, okay. It is the second electrolyte, and this material has better surface exchange behaviors compared to the other materials. These materials have super high ionic conductivity, and when it's contact with the cathode material and the air phase, gas phase in there, the exchange reactions accelerated a lot. Basically, oxygen intake is higher than the other components. So you can pump more oxygen through the electrolyte if you use a bismuth-based electrolyte.
Oh, okay.
So net currents of the cell produced gets higher, and you get better performance.
You can make an experiment without Hafnia RBA or?
Yeah, I also did. There's a single electrolyte here. Oh, I mean, you mean in the material? What does the Erbia and Hafnia does? Okay.
Yeah.
These materials, Erbia increases the number of the vacancies, oxygen vacancies, and Hafnia is there to stabilize the phase for long term. Because these bismuth-based materials shows aging or phase change during their operation, and Hafnia is basically there to stop it and make it more stable. We will work on long-term performance and see what happens, but for the beginning, it is pretty good, I can say that.
Yes, thank you. Yes.
No problem.
Okay. The next presenter is Mustafa Çelik. I think Mustafa Çelik is here. I couldn't see the Mustafa Çelik. Okay. The next presenter, Merve Albayrak, Ahmet Önal from and its presentation title, High Durable Rhodium Nanoparticles Supported on Titania as an Electrocatalyst for Hydrogen Evaluation Reaction via Electrochemical Water Splitting. I see the Merve is here.
Yes, I am here.
Okay. Can you share your presentation?
Yes, okay. At Chemistry Department, today I'm going to present you a highly durable rhodium nanoparticle supported on titania as an electrocatalyst for hydrogen evolution reaction via electrochemical water splitting. In this study, the preparation, characterization, and investigation of electrocatalytic activity of rhodium titania towards a hydrogen evolution reaction are presented. After impregnation and reduction of rhodium-3 ions on the titanium surface, according to the ICP-OS analysis, rhodium metal content of rhodium titanium was determined as 0.5% weight rhodium weight. Rhodium titanium was also analyzed by transmission electron microscopy, TEM-EDX, and X-ray diffraction analysis. The obtained catalyst was attached to surface of glass carbon electrode rope-wise. For all tests, the rhodium amount on glass carbon electrode kept constant as 3.79 microgram per centimeter square. For all electrochemical studies, 3 electrode systems were used. Modified glass carbon electrode, silver chloride, and platinum wire as a working reference and counter electrode used respectively. Transmission electron microscopy analysis was performed to investigate the size of rhodium nanoparticles. As seen in figure 1A and B, highly dispersed rhodium nanoparticles with the 2.54 nanometer mean particle size were formed on the titania. Also, transmission electron microscopy EDX analysis given in figure 1D confirms the presence of the rhodium nanoparticles on the surface of the titania. However, due to the 0.5% weight rhodium loading, there is no peak indicating the rhodium nanoparticles in the X-ray diffraction spectra in figure 2B. According to the X-ray diffraction results of titania and rhodium titania, there is no change in the crystal structure of titania after rhodium impregnation. The electrocatalytic activity of rhodium titanium modified glass carbon electrode was investigated by the recording polarization curves in 0.5 molar sulfuric acid solution. Since the electrocatalytic activity of modified electrode was found to be improved gradually after potential cyclic between minus 0.5 and 0.5 volt versus silver chloride, rhodium titanium modified glass carbon electrode was subjected to the potential cyclic until no more change was noted in the onset potential. This point was reached after 2000 cycle of cyclic voltammetry treatment in 0.5 molar sulfuric acid solution to check if glass carbon electrode or bare titania without rhodium show any activity in hydrogen evolution reaction. 2.5 microliter of rhodium-free alucat was dropped onto the polished glass carbon electrode, and without rhodium, bare glass carbon electrode and titanium shows low activity towards the hydrogen evolution reaction. The improvements in the electrochemical activities of titanium and bare glass carbon electrode were observed in control experiments. These improvements can be attributed to the cathodic deposition of the platinum originating from the anodic dissolution of platinum counterelectrode. Note that there is no improvement after 2000 cycles for the rhodium titania. The polarization curves belong to the bare glass carbon electrode, titanium and rhodium titania modified glass carbon electrode after the cyclic voltammetry treatments were presented in figure 3A, and corresponding tuple plots were given in figure 3B. Tuple slopes of the bare glass carbon electrode, titanium and rhodium titanium modified glass carbon electrode were calculated as 106, 87 and 32 millivolt per decade respectively in figure 3B. The overpotential values at 10 milliampere per centimeter square current density for rhodium titanium and titania were found 37 millivolt and 104 millivolt versus reversible hydrogen electrode. The lower rhodium titania, the lower onset potential of rhodium titania makes it superior over the most of the reported rhodium-based catalysts. The durability of rhodium titania was tested by applying 10,000 cyclic scan at a scan rate of 50 millivolt per second in sulfuric acid solution. The polarization curves which were obtained before and after the stability test indicates that there is a negligible change in the onset potential, overpotential, and tuple slope. According to these results, one may conclude that rhodium titanium is highly durable electrocatalyst and provides superior electrocatalytic stability in hydrogen evolution reaction as compared to the rhodium catalyst in the literature. The volume of the evolved hydrogen gas from the water electrolysis was measured in Hoffman electrolysis cell and followed as a function of time. The Faradaic efficiency of rhodium titania for hydrogen evolution reaction was calculated as 94% after applying the charge of the 18,000 millicoulomb. The calculated yield is also consistent with the theoretical one. Electrochemical impedance spectroscopy method was also studied to determine the electrocatalytic activity of rhodium titania at different potential. The observed semicircle at low and high frequency regions in figure 6A and B can be fitted to the model, inset model. The semicircles at the high frequency region is potential dependent, and its radius decrease with increasing potential, indicating faster charge transfer occurred at higher potentials. And the semicircles at low high frequency regions are potential independent and arise from the contact between the glass carbon electrode and the metal and the electrocatalyst. Also, the tuple slopes can be calculated by using the impedance spectroscopy results. This calculation method is only related to the charge transfer kinetic and allows to exclude contribution coming from the catalyst resistance. And from the onset versus logarithm of 1 over charge transfer resistance plot shows that the toughest slope value was calculated as 33 millivolt per decade, which is quite similar to the one derived as the linear speed voltammetric curve. As a result, rhodium nanoparticles were successfully formed on the surface of titania and characterized by various analytic techniques. Onset potential, Tafel slope, and overpotential values of rhodium titania decreased drastically after 2000 cycle treatments by using the platinum as a counter electrode. The observed improvements in the electrochemical activities of the titania, bare glass carbon electrode, and rhodium titania during treatment can be attributed to the catalytic deposition of the platinum originating from the anodic dissolution of platinum counter electrode. The amount of platinum deposited on rhodium titania on glass carbon electrode after 500, 1000 and 2000 cycle were determined as 0.52, 6.38 and 17.94 platinum to rhodium mole ratio, respectively, by using the ICP-OS spectroscopy. The observed improvement in the electrocatalytic activity of rhodium titania 2000 can be attributed to the not only the platinum deposition but also the rhodium platinum interaction. Note that there is no improvement after 2000 cycle for the rhodium titania. Rhodium titania 2000 provides very low Tafel slopes, 32 millivolt per decade, low over potential, minus 37 millivolt at minus 10 milliamp per centimeter square, and high exchange current density, 0.686 milliamp per centimeter square, and high turnover frequency values. The periodic efficiency of rhodium titania 2000 was found 94% after applying the 18,000 millicoulomb. Rhodium titania 2000 on glass carbon electrode provides high stability even after 10,000 cycles in hydrogen evolution reaction. There is no noticeable change in the onset potential, over potential, and Tafel slope after the stability test. All these results indicate that rhodium titania is a promising electrocatalyst towards the hydrogen evolution reaction. Thank you for your attention. This is my reference list. If you have any question, I will be glad to answer.
Thank you, Merve. You have
welcome, hocam.
You have one question.
Okay.
The Razal asks you how to confirm the presence of rhodium in the rhodium titanium sample. How to confirm the rhodium?
With transmission electron microscopy and ICP. ICP the amount. With ICP, 0.5% rhodium in rhodium titanium.
Is that analyzed by XPS?
Yes, we did XPS analysis. Rhodium 0 and rhodium class 3 were observed in the XPS spectrum. However, I didn't show that.
Okay. I think you answered the question. Okay. If another further question, I think you're the last presenter. Yes. This is the end of our section, and also this is the end of our conference. I would like to thank you all participants and your valuable contributions. I also thank to organization committee and Professor Dr. Yasemin Çiftçi. I wish you healthy and beautiful days. And now I give the words to Yasemin Çiftçi, Professor Dr. Yasemin Çiftçi.
Okay. Hello.
We see you. We see you and we can hear you.
Okay.
Okay.
I will open the camera. Dear participants and guests, the third International Hydrogen Energy Congress and Exhibition, the first two of which were held in Istanbul, has completed successfully this year in Ankara with the hosting and support of Gazi University. Thanks to you, our esteemed participants. We express our endless gratitude to all of you. I would like to thank the technical team and organization committee for their efforts during the Congress and the organization stage of this Congress. I would like to thank Gazi University and all our sponsors for their contribution and providing the success of the Congress. Although there were minor setbacks, our Congress was successful in general. We apologize for the inconvenience experienced. After the Congress, the publication selection stage will begin and you will be contacted. I would like to remind you that the selected article must be written according to journal rules and will go through the review process. You or esteemed participant who participated with the total 114 papers from 15 different countries and presented their valuable work honored us. As the organization team, I would like to express our regards. Thanks again, all of you. We wish you healthy days. Regards. Thanks again. We closed our Congress. Thank you for all participation and listeners.